I have to go to one point whatever I told. I told the transistor names comes from the word called transfer plus resistor. Correct? Transfer plus resistor. Now if you look into your board, your notebook, you can see you have drawn the depletion region width. Okay, left side depletion region width is less, right side more depletion region width. Depletion region is become wider and wider because resistance is higher or lesser? More depletion region means more resistance or less resistance? More resistance, because carriers cannot cross junctions. So now if you see, one side less resistance, other side more resistance. So resistance are transferring. Transferring means what? Changing. Transfer means change. I got transfer from here to here means I am changing. So resistance is changing from low to high value. That's what it is called. Transfer plus resistor is called transistor. Understood? Huh? This you just understood. You don't want to write because there is a transfer of resistor. So just to write one point, then should be there. Just write a note. Transistor names comes from the two words. Transistor names comes from the two words. Transistor names comes from the two words transfer plus resistor. Transfer plus resistor. Okay, which means that what? Which means what? Which means right below, right, which means transfer of resistance. Transfer of resistance. Resistance transfer idu change ayi. Transfer of resistance from low emitter base junction resistor to low emitter base junction resistor to high collector base junction resistor. High collector base junction resistor. You got my point, right? We are transferring the resistance from lower value to a higher value. That is a word called transfer resistance. Now you got the meaning of what is called BJT, bijunction transistor. Two junction transfer of resistance are happening. This is how the transistor name came. Okay, go to the next topic. Output characteristics of the transistor. Output characteristic. Write on Shakti Prakash. Output, correct Dana? Shakti Ganesha? I forgot your name. Output characteristics. What's your name? No, his name. The yellow shirt. Correct? Huh? Okay. Output characteristics. Output characteristics of a transistor. Okay. With a transistor and output current output current IC, output voltage VCE. So right, it is the plot between output current is a plot between output current IC versus output voltage VCE. For a fixed value of input current, IB, for a fixed value of input current IB. Okay, so draw this graph also. IB, not IB, IC versus VCE. IB equal to 0 microampere, IB equal to 10 microampere, and so on, and IB is equal to 100 microampere. Output characteristic is the plot between output current and output voltage for a fixed value of input current IB. Okay, so what we have done in the previous circuit also, you have seen we have a VCC is there, right? In the circuit we have drawn circuit diagram, VCC, ammeter, voltmeter, the diagram in which we have drawn voltmeter, ammeter, the VCC is changing. Okay, whenever if you change VCC, can you tell me the equations, can you do a KVL there? KVL means plus, okay, what is this voltage will be here? VCE. Here what is there? It's plus minus VCC. Now can you do a KVL here? And this is IC and this is RC. Can you do a KVL here? Will be here, what will get? VCC minus 2 plus VCC minus IC RC minus VCE 0. So VCE equal to what? So to change VCE, what should I want to change? VCC. This is a variable. So whenever you change VCE, again we will create a tabular column. There we will mark two things. First one is IC for VCE. So 0 volt, we will see what is the value will be here, maybe 0, 0.1, we will maybe 0.4, we will see 0.2, maybe 0.8, we will see 0.3, like this, etc. Okay, for a fixed value of IB. Once you plot the graph, we can see the graph looks like this one. For different values of VCE, IC graph we have marked and we have drawn for every values of IB. For example, maybe this tabular column is for example, IB is equal to 30 microampere, IB fixed, and we have created one tabular column like this. Similarly, I changed IB into 40 microampere, then again I created a table, then again I have drawn. So for different values of IB fixed, IB 10, I have created one table and I have drawn the graph like this. Then I changed IB is equal to 20 microampere. Same table I have created. By changing VCC, VCE will changes, IC will changes. So the next line, IB is equal to 20 microampere, 30 microampere, 40 microampere. For different values of IB, I have created. Now here 0 to 100, almost 10 tables I have drawn. Based on this one I got it. Next, what is the speciality or the significance will be here? This is important. You see, VCE collector emitter voltage is forward biased or reverse biased? Collector is forward or reverse biased? Reverse biased. Okay. Now if you come, the graph will have a 3 sections, 3 area. The first area is the line below IB. When IB is equal to 0, transistor is a current controlled current device. Where current control means current is controlling the current device. So when IB is equal to 0 means I am not giving any current to the transistor. Then what will happen? Is dead. Transistor will not work because IB is the current to the transistor, right? In a transistor structure, collector, emitter, base. So this is the collector, this is the input, base, this is the output, collector, this is ground, common emitter configuration. So here if I am not giving any input current, transistor is dead. That dead situation is called cut-off region. This graph, this region is called cut-off region. Just listen one moment, we will write. This is what region? P region, N region, N regions. N region. So here initially I have given what voltage? Positive, negative, like this. Correct? Now I have not given any voltage, which means this is not disconnected. Earlier the other side is what connection? Earlier this side is what connection? Forward bias. The output side is what bias? Reverse bias. Now forward bias will happen if I am giving voltage. If I am not giving voltage, any forward bias will happen? No, nothing, because I am giving anything. That nothing condition is considered as reverse bias because I am not giving anything, because transistor is dead. So the input side and output side both will be falls under what region? Reverse region, which means transistor is completely dead. Two junction reverse bias and junction will not work. side forward it should work. Both side reverse bias means both side depletion region, both side it is like a diode, like diodes are connected back to back. Two diodes are in reverse bias condition. Diode will work. Both diode dead. Both diode dead means transistor is dead. If transistor is dead means that condition is called cutoff region. Transistor is not working. Next, another one is VCE. This is the axis in which VCE is increasing. When I am reducing VCE like this, if I am coming from right to left, at this line if I am taking VCE value is very less. VCE means what? VCE is the collector emitter voltage I am giving. If this voltage is 10 volt, now I am reducing to 0.1 volt. So which means that what? Reverse bias voltages is very less. Suppose here I am giving the forward voltage, forward bias I am giving, the positive with the negative, positive negative, forward bias I am giving, 5 volt battery. Here I am reducing the VCE, collector emitter voltage I am reducing means reverse bias increases or decreases. Let's go once again. Transistor, okay, NPN, let me put it like this, NPN, and this is your emitter, this is your base, this is your collector. Now the emitter base junction, this is one junction, and your collector. So collector, so two junction for a transistor, right? Collector base junction is what biased? Reverse bias. So collector should be connected with the positive and base is connected with the negative. So this is what bias now? Reverse bias. And emitter is what bias? Forward. So negative, positive, connected like this, for example. So now this is forward bias. Okay. So this is, now I can also say collector is connected with a negative terminal. So collector is in reverse bias state, but this is in forward bias. So here reverse bias means VCE, the collector. This means VCB, right? VCB. This means VBE, right? VBE. So I know VCE is equal to, tell me, VBE plus VCB. Okay. Now I say what will reduce here? VCB will reduce. VCB will reduce means what is reducing? Reverse biasing reducing. Reverse, finally it become what? It becomes 0, then it become forward bias. So this is the region at which collector base junction is forward bias. So I can say collector base junction forward biased, emitter base junction is also forward. This is both regions are forward biased. Okay, and this region of transistor is called saturation region. Saturation. Transistor can't do anything. I saturated. I attended 12 hours of class, then I saturated. We'll say, right? Beyond that I cannot afford. So similarly, saturated. Transistor cannot do anything. Transistor maximum reached. So saturation region, cutoff region. Cutoff is what? Transistor is off. രണ്ട് റീജിയനും റിവേഴ്സ് ബയാസ് ആയിരിക്കും. ഇതിൽ രണ്ട് റീജിയൻ ഫോർവേഡ്, കാരണം VCE റെഡ്യൂസ് ചെയ്തു. VCE റെഡ്യൂസ് ചെയ്യുക മീൻസ് റിവേഴ്സ് ബയാസ് ഇങ്ങനെ റെഡ്യൂസ് ചെയ്ത് പോകും. റെഡ്യൂസ് ചെയ്ത് പോയാൽ ഫൈനലി ഇറ്റ് ഈസ് കൺവേർട്ടഡ് ഇൻ ടു ഫോർവേഡ് ബയാസ്. അതാണ് അതിന്റെ എൻഡ്. അപ്പുറം ഇനി വൺ റീജിയൻ വിൽ ബി ഹിയർ, ദിസ് റീജിയൻ. What is happening this region is the real working is happening, right? Here is the major part of the graph. This region is called active region of the transistor. Active region. In this region, the normal thing, what is the normal thing? Here it is forward bias, here it is reverse bias, which means emitter base junction forward biased, collector base junction is reverse bias. This is called the active region of the transistor. So moon region, cutoff region, active region, saturation region. One more region will be there, that I will tell you later. Okay. So saturation, cutoff. Why it is called cutoff region? Both are reverse biased because transistor is completely dead. It will not work. It is a useless device, like a bulb fuse, and it is useless. Transistor is useless. Why this region is called saturation? Because both are forward. How collector, emitter base is already forward. How collector base become forward biased? Because at this line, the small value VC is very reduced, very less value. VC higher value means higher reverse bias. Higher. When VCE comes down, down, down means when come to the complete side of the left graph. From here to here, completely to here in the left side. So when you come will be here. This is a VCE. VCE in the actual value is what? Actual value is the reverse bias voltage. When you decrease the reverse bias voltage, what you will do? You will come to this side of the graph. Then it become what bias? Forward. So all this region towards left side is called saturation. Bottom cutoff, right side is active region. Can you draw this graph? It's hard to draw, I know, but understood, right? Okay. Many things will be there. Okay, only draw the graph and mark the region. Collector base, forward bias. Hope you already drawn, right? Okay, then in the same graph you can mark collector base, forward bias. Just a dotted line, just on the shade east side. Just to give in the existing graph itself, just to shade this region. Then say collector base forward biased, emitter base forward biased, saturation region. Same graph wherever you have drawn the same graph. Then next active region, emitter base forward biased, collector base reverse biased. That active region. Below it is cutoff region. Cutoff region means emitter base junctions reverse biased because there is no current, and collector base is always in the reverse biased. Emitter base junction reverse biased, collector base junction is also reverse biased. Collector base is already reversed when IB is 0 or IB less than 0, which means collector emitter base junction is reverse biased. Transistor is in off condition. Okay, we'll see transistor has a switch after some time. Okay, collector base junction. Okay, then create one tabular column. First column emitter base junction. Second column collector base junction. Third column region of operation. Emitter base junction, collector base junction, region of operation. 3 tabular column. 3 column or heading. Okay, emitter base junctions, collector base junction, and this one. Okay, emitter base junction forward biased, collector base junction forward biased, and it is called saturation region. Next one, emitter base junctions forward biased, collector base junction is reverse biased, then it is called active region. Okay, next one. This is opposite. Reverse emitter base junction reverse biased, collector base junction forward biased. This is not there in this graph, and this is called inverted region. Just active into opposite and inverted. Simple. Next one, already in the graph, reverse bias. Two reverse bias are the cutoff region. So saturation active, cutoff is available in the graph. Other one we cannot plot in the graph. Okay, forward bias saturation, forward reverse active, reverse forward inverted, reverse cutoff. Okay. Below right, transistor configuration overview. Transistor configurations overview. Transistor configuration overview. Transistor configuration. How many transistor configuration? Common emitter, common collector, common base. Three configurations. So first we line CE, common emitter, common base, CB, common collector, common emitter, common base, common collector. This common emitter exam by chance side you have to write. Okay, so emitter, common emitter is grounded. Okay, common emitter means emitter is grounded, and this is the input. Input is what? Input is IB and output is IC. IC, and this is IE. This is common emitter grounded. In a common base load varumo, base is grounded, base in a grounded, emitter here and collector here. So IC and IB, okay, and emitter. IB. Base is grounded, common base. Next one is common collector. Common collector la, this is the input, emitter is the input, base is the output. Wait a second, IC has to mark. IE is always outside, the directions is changed. IE, because IE like this, IB inside, IC inside. This is IE, emitter. Two incoming current, IC plus IB equal to IE. Okay, so here this is the input and here this is the output. Common emitter, this is most important. Input, and here this is the output. This is the most important, others two are less chance to ask. Okay, this is most important. Common emitter is most important, others two are chances are less. One second, this is input. I wrongly marked input is output, sorry. Left side is always input, output, output. Okay, left side is input, IB is input, IE is the output, collector is grounded. Common emitter means emitter grounded, common base means base grounded, common collector means collector grounded. Okay, next factor is current gain. Current gain means what? Output current by input current. So current gain equal to output current divided by input current. That's current gain in the definition. Common emitter la current gain is representing using a letter called beta. Beta. What is the output current will be here? IC, right? So IC divided by IB. This is important. So beta equal to IC divided by IB. This is important. You may get one question. Second one, base configuration. Current gain alpha equal to IC, output by input, IC by IE, output by input. This is alpha represent. This is gamma, current gain equal to output by input, IE by IB. Okay, then finished, back. Then write the next heading, relation between alpha and beta. 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 So we have two equations will be there, right? Alpha and beta. So what is the emitter current equation? IE is equal to IC plus IB for all transistor configuration. Dividing with the IE everywhere. Sorry, dividing with the IC everywhere. So I want to cancel IC. IE by IC is called 1 by alpha, reverse. Correct? IE by IC is called 1 by alpha is equal to 1 plus. IB by IC is called 1 by beta. Now I am taking LCM and I am simplifying. 1 by alpha minus 1 equal to 1 by beta. Okay, can you simplify? Can you tell me what is beta equal to? And then the formula you have to write. So 1 minus alpha divided by alpha equal to 1 by beta. LCM eduthu. Then beta equal to alpha divided by 1 minus alpha. 1 minus alpha. Beta divided by 1 minus alpha. Standard value of alpha is 0 less than or equal to alpha less than or equal to 1, which means alpha lies between 0 and 1. Okay, beta value 100,000 normal conditions. They will give you the question, you don't want to take it, but I am telling just for your informations. Beta value 100 to 1000. Okay, now sir, this is the real pain area. Okay, so write one question below. For the given circuit, then we'll draw the circuit diagram. You can also draw along with me. For the given circuit, for the given circuit, then draw the diagram. given circuit, the value of IB and VCE are dash. This is how they will ask. Okay, I'll solve this, then I will give you the next one for you to solve. Okay. Okay, so the first one here, the basic fundamental is that I have to apply KV, Kirchhoff voltage law. First questions to you, how many loops are there in the circuits? How many loops are means one loop, one KVL equation I can write, right? One Kirchhoff voltage law equation I can write. How many KVL equations I can write, or how many loops are there in the circuit? 1, 2, 3, 4, 5. Tell me how many loops? Visibly one will be there. This is visible, but there are other. What are the things? Loop means high one voltage to ground level. If you can come voltage to ground, then that is a loop. That's all. How many? This is one loop, right? This is positive. You can come negative. So that is a loop. Another loop, VCC 10 volt. You can straight away come to ground. So this is the second loop is here. It's not like a path, but it is a loop. Correct? VCC voltage you can go to ground. Then the straight way is one loop. This is another loop. This voltage you can go to ground. One more loop will be there. What is that loop? So this is my loop 1. Okay, and from 4 straight to down, my loop 2, and I have one more loop will be there like this. It's coming like this outside. So this is my loop 3. So what we required, based upon that we have to write the loop equations. Okay, now actually I need 2 loop equations to solve it, but I will write the 3 loop equations. Can you tell me what is the loop 1 equation? Loop 1. If you want to draw, or if you want to take loop 1, what you have to do means you just duplicate it. Okay, so just duplicate it means plus. This is how much? 20 volt, and here resistance IB is coming and RB is there. We can substitute the value. Then what is there here? Base emitter junction. Base is what biased normally? NPN, PL. So forward bias. Appo a positive voltage first. Idana base. Appo base il oru voltage undayikka plus minus ingane. Plus minus. Appo plus minus. Idu connect chedu. Idana loop 1. This is called VBE. What is the value of this one? 0.7 volt. Now you can write the loop equations. Tell me what is the loop equation? 20 minus IB RB minus VBE is equal to 0. VBB is 20. IB is how much? It's not given. We have to find out. IB into RB is how much? 50 minus 0.7 equal to 0. You have to solve this and find the value of IB. Okay, this is loop 1. So loop 1, please write loop 1. IB is equal to 19.3 divided by 50. This is enough to do. Okay. This is whatever the value in my mind have placed in real entrance examination, it will cancel. Maybe some 100 divided by 50. Very easy. They are not checking your calculation skill, right? Next one is what? Loop 2. Second loop. Second loop is where? There. VCC means manual voltage. So manual is positive. First positive, then negative. This is loop. Okay. This is voltage. Okay, so voltage plus minus. What I am going to do means plus negative. This is VCC. Just not to confuse this one. Plus it's there and then negative. So here total voltage will be equal to VCC. Correct? VCC. What I am going to do means I am drawing like this. VCC. Then what other things will be there? Resistance. What is the value of resistance? RC. Then collector emitter. Then collector emitter. What is the voltage will be here between these two? VCE. Collector is positive or emitter is positive? Collector is positive or emitter is positive? Collector is reverse biased, normal case. Collector is NPN transistor. Collector N. What we have to give? Positive. So it is positive. Negative. If the polarity change, the answer will change. So it is connected like this. And this is the VCE. This is emitter. This is collector. So this voltage is called VCE. Can you apply the loop 2 and tell me the equations? Tell me loop 2 will move like this. Tell me the loop equations. Tell me. VCC minus current IC. ICRC minus VCE equal to 0. VCC is given in the question 10 volt. IC is given in the question 10 milliampere. So 10 into 10 power of minus 3. RC is given 1 kilo ohm. So 1 into 10 power 3 minus VCE equal to 0. So VCE equal to 0 volt. So only 2 loops are enough, right? Third loop is not required. Just for sake of interest, what is loop 3 equation? Loop 3, can you tell me loop 3? What all the things will be there? We have to come like this one, right? So VCC. So VCC means upper side positive, then negative. So this is VCC. Then what is coming? RC. So there is one RC will be there. So I am drawing as RC. Current is coming through is IC. Then we are going in this way. So what is will be here? VCB. C is positive or B is positive? Why B is positive? C is also positive, right? C is connected with a battery. This is the collector terminal. This is connected with the positive, right? Collector is connected with the positive. Base is also connected with the positive. Correct? VCC. C collector is connected with VCC. VCC. This is collector. This is the collector wire. Correct? This is a collector terminal. This is connected with VCC. Collector is connected to positive. Okay. Then you have a base is also there. Base is also connected with the positive. So which one is positive? In this case, what you have to do means you have to look into the voltage of each one. Okay, voltage of each one means this is a ground, right? VCE voltage means what? Voltage of collector with respect to emitter. What is the voltage of collector with respect to emitter? 0. So which means here 0 voltage. Keep it in mind. VBE voltage of base with respect to ground. How much here? 0.7. So which one is higher? 0.7 is higher. So base will act as positive, collector will act as negative. So first we have to draw collector. So now this is base above collector. So collector is negative, base is positive. Now this is your VCB. Then what is coming? Now you are here. Now what is will be there? RB. So RB. Then you are coming down. What is will be here? 20 volt. So 20 volt. That's all. Yes. Now it's going to ground. So now these two are connected. This is your next loop. Okay. We'll write the equation. Tell me the loop equation, sir. VCC minus IC RC plus VCB, correct? VCB. Then RB kada varumo current, RB inde current edukkanam. IC RB same alla. Aa loop il same aanu, but ivide varumbod current change aayi. What is that current? IB. Karanam idu rendu section aanu circuit inde. So ivide varuna current IB current aanu. Karanam idoru part, idoru part. This current IC. This current IB. So we have to write minus IB RB. Then what extra? Minus 20 is equal to 0. That's all. Okay. Just for your understandability. That's all. How to write the loop equation. How to decide. Collector is positive, base is positive. So which one is more positive? That will give more positive. Okay. In this case, collector is 0, base is 0.7. So base is more positive than collector. That's base is positive, collector is negative. Some cases it is reverse. Depends on the question. This is normally loop 3 and the complex but you want to know how to write. Below write the possible loop equations. 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 Write the possible loop equations.
VC terminal கண்டுபிடிக்கிறது. எப்படி கண்டுபிடிக்கிறாங்க?
പോസിറ്റീവ് നെഗറ്റീവ് ആണോ? എമിറ്റർ ഗ്രൗണ്ട് തന്നെ, സോ അത് എപ്പോഴുമേ നെഗറ്റീവ് ആയിരിക്കും. കളക്ടർ എപ്പോഴുമേ പോസിറ്റീവ്. അതാണ് VCC. VCC is connected to collector, so collector is always positive, emitter is always negative. Okay, collector is always positive because it is reverse bias. അതല്ലേ ട്രാൻസിസ്റ്റർ വർക്ക് ചെയ്യുന്ന സ്റ്റേജ് എന്ന് പറഞ്ഞാൽ ഫോർവേഡ് ബയാസ്, റിവേഴ്സ് ബയാസ്, ആക്റ്റീവ് റീജിയൻ. സോ കളക്ടർ ഈസ് ഓൾവേസ് കണക്റ്റഡ് ടു VCC. ഈ ഡയഗ്രത്തിൽ എമിറ്റർ ഈസ് ഗ്രൗണ്ട്. ഗ്രൗണ്ട് എന്ന് പറയുമ്പോൾ അത് നെഗറ്റീവാണ്, അതർ വൺ ഈസ് പോസിറ്റീവ്. അതാണ് VCE. C പോസിറ്റീവും E നെഗറ്റീവ്. ഓക്കെ, നൗ ഹൗ മെനി ലൂപ്സ് ആർ there? 1 2 only 2 or 3? Okay, so because all you don't want to learn, at least can you tell me 2 loops? 2 loops, whatever you are saying. VCC, RB, VCC, RB, adukapra IB means this line, then ground. So this means one loop is coming like this. Okay, this is loop 1. At least you are able to write this one. What is next loop? VCC, RC and IE. This is loop 2. Good. This is at least, if you want you can consider here also, but it's not required. These 2 are sufficient to answer the question I'm going to ask you. Okay, now can you write this loop equations? First we will write loop 1. Loop 1. By looking to the circuit, so just listen. Normally we can go and redraw the circuit. Okay, instead of doing that, in one step we can write, see, listen 1 minute. VCC is the voltage given to the circuit. Okay, this VCC, in one step you can answer. This VCC are used by, who are now this VCC are using? One is IBRB. That is a voltage is losing here as heat energy. Okay, so IBRB is using. So VCC, you are giving some energy, battery, and it is used by heat energy here. Then balance heat energy will be here also, VBE. So in one shot you can write VCC is your total energy you are giving, and it is used by IBRB as heat energy plus VBE. These 2 are together used by the VCC. Both are losing heat energy. So loop 1. Now we come to loop 2. Without drawing the circuit we can save some time. Similarly the output side, who are all using? ICRC is using, then VC is using. So VCC equal to ICRC plus VCE. That's all. Okay. Without drawing the circuit, you assume the supplied voltage given by you is used by all the elements in the circuits. Below, write one question. Next question. In the circuit shown below, current gain beta equal to 100. In the circuit shown below, current gain beta equal to 100. What should be the base resistor RB, so that base resistor RB VCE equal to 5 volt and VBE equal to 0 volt. and draw the circuit diagram. This is a circuit which is given. So transistor, emitter connected, and base RB and RC. $100 1 kilo ohm. Okay, what we need to find out? RB, base resistance in the value we have to find out. 1 kilo ohm is given and RB 100 volt is given, that's all. No IC, nothing. But extra one factor is given. What is that? Current gain. Beta is given 100. So how to do? Always if a transistor question is coming to you like this or any way, first write the loop equation possible, then everything will strike to you. Okay, blindly write the loop equation, then things will come to you. How many loop equations will be here? Similar to the previous one, this question, right? VCC earlier we connected on the top, this is we just tilted here, both are same. How many loops equation? At least we can write 2. So what is the first loop equation, sir? Left side. Blindly start with the loop equation, sir. You will get the answer at some point of time. Loop 1. Okay. Loop 1. So what is the total voltage is given there? 100. It is used by IB, RB plus VBE. Correct? So loop 1 voltages are used by whom? IB, RB and VBE. So VCC given voltage, the VCC is given from the top like this. Here also VCC, right? 100 volt. VCCs are used by IB, RB plus VBE. VBE given in the question. How much VB is given in the question? 0. So VCC is 100 is equal to IB into RB plus 0. Okay, so I got IB, RB is equal to 100. So just keep it there. Equation number 1. That's all. We will see what's coming. Loop 2. Second loop. Second loop is where? Second loop is here in the straight way down, right? Loop 2. Can you tell me loop 2? VCC. VCC is a voltage giving on the top. VCCs are used by whom? IC, RC plus VCE. What is VCC? 100. What is IC? I don't know. What is RC? 1 kilo ohm. So which means 1000 plus VCE is how much? 5. We can find IC, right? Now we got some hint. First equation nothing to do, but second equation we got IC. IC is equal to 95 divided by 100. Sorry, 1000. So which means I can say 95 milliampere. Correct? Doubt? No. Any doubt? No. So IC equal to 95 milliampere. Got it? Okay. IC equal to 95 milliampere. Now what is given in the question extra? Beta. Current. Beta equal to what? IC by IB. So what I can find from here? IB. IC by beta. 95 milliampere means 95 into 10 power minus 3. Beta is how much? 100. So it become 95 into 10 power minus 5, or I can say 9.5 microampere. 9.5 microampere. Or 95 into 10 per ampere. You can keep it like this. This is also fine. 95 into 10 per minus 5 ampere. Next, what I need to find out? RB. For that, what should I do? First equation is substitute. Straight away, right? You will get something on the run. Okay, now we'll substitute on equation number 1 become 100 is equal to IB. 95 into 10 power of minus 5 into RB. So 100 divided by 95 into 10 power minus 5. So it becomes 10 power 7 divided by 95. Okay, this is the value of RB. You got it up? Same thing.
1.04 into 10 power.
Okay, that is okay. 1 by 95. You solved this one, right? That's all. Okay. So 10 power 7 divided by 95. Okay. So this way the questions will come. Okay. So you have to straight away, nothing is striking, no problem. Straight away go and write loop equation. You will get something at some point of time. Okay. Next one. Application of transistor. Application of transistor. Application of transistor. How many applications we are going to learn? Number, how many? Transistor use, one application, wherever transistor is using. Application of transistor. Transistor in 3 application. Transistor as an amplifier, transistor as a switch, transistor as an oscillator. Okay, I'll first one. Transistor as a switch. Transistor as a switch. Transistor as a switch. Transistor is working as a switch. Okay. Okay, so let's draw the circuit diagram first, then we'll try to explain. So it is an NPN transistor, and marking here, supposed to mark here, output, this is input. Collector reverse bias, base forward bias, VBB, VCC, then V out, V in. Okay. Transistor as switch. Switch means what? Two position, on position and off position. That's what we are going to see. So first we have here plainly we have how many loops be there? 2 loops. This is loop 1. Now the loop equation everywhere we are going to use, and this is one is loop 2. Okay, we are going to write the loop equations. Now you know the basics. Loop 1. Can you tell me what is the loop 1 equations? We will write. We will do it like this. So the order is same. Loop 1. Tell me what's the loop? VBB equal to IB RB plus VBE. Correct? This VBB is also called the input voltage. So VBB is replaced with V in equal to the same thing, IB RB plus VBE. This is given as equation number 1. Write it. Equation. Next, loop 2. Loop 2 equation is what? How the loop 2 is coming? This one. VCC is the voltage given which is used by ICRC and VCE. So VCC equal to ICRC plus VCE. That's all. Okay. Next, what is output? VCC. VCC is a given energy, ICRC is the used energy, VCE is also the used energy. Okay, so VCC minus ICRC, this is equal to what? VCE. So you are giving VCC and you are giving some voltage and it is used by RC, and the difference, you are giving something and it is used by something, balance you will get, and this balance is called V out, and this is actually equal to V out. Okay, VCC minus ICRC equal to V out, and that is nothing but what? VCE. That is called the V out. Okay, so this is equation number 2. Okay, now what we are going to do, we are going to draw a graph between V out and V in. V in is the input voltage I am giving, V out is the output voltage I am getting. Correct? These two are the things. So these two equations are my only the mathematical steps. Input is initially 0. Input is 0. Input is 0 means input is 0 or closely equal to 0, VBE, that is fixed points, very less value. But what should be will be here 0. If I am not giving any voltage, VBB equal to V in. If I am not giving any voltage, value of IB. Okay, when IB equal to 0, what is the value of IC? Okay, so let's put when IB equal to, okay, so V in equal to 0. V in equal to 0 means VBB equal to 0. I am not giving any voltage. If I am not giving any voltage, IB equal to what? 0. IB equal to 0 means IC equal to what? Beta IB. Beta IB. Beta will have a value, that is a transistor property. But IB 0 means IC equal to what? 0. If IC equal to 0, what is V out? V out means what? VCC minus ICRC. So VCC minus 0 into RC. What should I get? VCC. This is case number 1. So when input is equal to 0, output is how much? Output will have a value. What is that value? VCC. Okay. So this is one part of the discussion. Second part. So now V in 0. Now what I am going to do? I am going to increase V in. If I am increasing V in, first listen, then we can write. If I am increasing V in, which means what is increasing? VBB increasing. So VBB increases. If VBB increases, what will happen to IB? IB increases. If IB increases, what happened to IC? IC increases. If IC increases, what will happen to V out? V out means VCC minus ICRC. IC increase and ICRC increasing. The more value I am subtracting. So VCC minus ICRC will decrease. So V out will decrease. So this will happen when I am going above. What will happen? V out will decrease. So how the curve will come? The curve is coming in a downward way. Like this it will come. Okay. So when V in increases, V out reduces. Okay, so you can draw the graph and write the things in the right side. write this also. Okay. Okay. V in equal to 0. When V in increases, VBB increases, IB increases, IC equal to beta IB, and V out reduces, and the graph will be coming down. Okay. Next, when V in equal to 0, okay, one more additional point here, right? When V in equal to 0, IB is equal to 0. IB is equal to 0 means transistor is off or on. IB equal to 0 means no current is not going to the base of the transistor. So off. Transistor is off. So transistor is off when V in equal to 0. That time what is the value of VCC? High. So which means this is one region of the transistor, and here transistor is on which state? Off state. This is transistor is on off state. Transistor is on off state. This off state is happening, that region is called cutoff region. That is called cutoff region. Off off. IB is equal to 0, output characteristics of a transistor. IB is equal to 0 below cutoff region. Next, V in increases. When V in increases, IB increases. Transistor is now turned on. Now the transistor is turned on and transistor is active. So now the next section of this line. This region, transistor is active. So this is called active region. This is called active region. So off state, cutoff region, and then active. Transistor is active because you are giving voltage. Now you increased. I told IB can reach as a maximum value. Pipe in a knob can reach as a maximum value. After that, can I able to increase IB? No. Only possible way is to increase IE. So when IB reaches the maximum value, what will happen when IB reaches the maximum? IB is very high. So IC is very high. If IC is very high means V out is very less. Okay, so transistor is reached on when IB is maximum. What is that value is called? Saturation. So this area is called saturation region. Saturation region. This is a maximum a transistors can do. Pipe in a knob and a maximum. Beyond that it cannot do anything. So this region, this is called saturation region, and this is called on state. So transistor will work as a switch. Switch means on off. In between off region and saturation region. In between an active region is there. Okay. So transistor can be used as a switch in cutoff region and in saturation. Saturation region it is on state. Maximum a pipe full on. Maximum water is flowing to the bucket. And another one is transistor is on off state. Pipe completely closed down. So no IB. If no IB means no IC. V out is max CC. So transistor is working as below, right? Transistor is working as a switch. Transistor is working as a switch. Transistor is working as a switch between cutoff region and saturation region. Between cutoff region and saturation region. This is very important. This graph is very, very important. Okay. So top side V in 0 on V in 0 on mouse transistor off on meaning. So off. Then transistor on. So maximum V in maximum IB. Maximum IB that is a maximum limit. So that is called the on state. Okay. Next one, transistor as an amplifier. Second application. Transistor as an amplifier. Transistor as an amplifier. Transistor as an amplifier, written in the heading, right? The same circuit we are also using there also. What is amplification? Amplification means ഒരു സിഗ്നലിന്റെ ഇത് ഇംപ്രൂവ് ചെയ്യണം. Improvements and magnitude improve. Now here see I am giving, this is what voltage? DC voltage, battery. DC voltage. This is also what? DC voltage, battery. Okay, using these two DC voltage I got it. This is the nature of the graph. Okay, now amplification means in a simple way, as you told, I have a signal suppose like this one, then I have to boost it and I have to make it as a bigger signal. This is called amplification, but there is no sine wave is given here, right? Okay, so now what happened means, in addition to the battery I will connect a sine signal here. So what actually I am doing here, I am not converting anything. Already one DC signal will be here. This is a DC battery. Then additionally I am giving a AC signal also. So what is actually happening? Addition of two signals, AC signal plus DC signal. Correct? So I am giving a small signal, but what I want at the transistor output, if I am keeping some oscilloscope, it's called oscilloscope. So adhe mari or instrument, if I am keeping it outside, I want this size of signal. This is what is my aim. So for that I have to give this input. Earlier there is no this signal, there is no AC signal, only DC signal. Only with the DC I got this graph. Now I am adding AC extra. Where I am adding? Which side I am adding? Input side. Okay, now we'll see if I am adding input side the signal. So this is the input axis, right? This is the input axis. So at the three place I can add the input signal. What are the three regions? Cutoff I can place AC signal. Suppose when transistor is on cutoff state, I can give this AC signal. Suppose transistor is on active state, I can give this AC signal. Suppose the transistor is on saturation state, I can give the AC signal. So AC signal will see three character of transistor or three behavior of transistor. What are the three behaviors? Cutoff, active, saturation. So how this signal will be producing output in three different situations. Okay, you can consider like a sad mood, happy mood, or an enjoyment mode, something like that. Okay, so during the three character of a transistor I am giving AC signal. Then I will see what transistor is doing. First I am giving AC signal when transistor is on off state. So AC signal means it is a pulse, right? So I'm taking just two lines. I am taking these two lines. Now I am giving input. Input means I am giving an AC signal like this. Okay, so this is an AC coming to AC axis, input axis. So where is the output? Output is this one. Output is this one, right? This line is corresponding to your output. Output is this one. So output, how you get output? Output is like, any difference between input and output? No difference. So if you put transistor in cutoff, then if you give AC signal, you will never get an amplified signal. Now what I have done means, I have taken the same point like this one here and one point like this here I am keeping. Okay, here I am giving the AC signal. So I have 2 points will be here. 2 points will be here. Now what should I get? I'll get here positive, negative, positive. Okay, here one property will be there that I will tell you a little bit later. Positive, negative, positive, negative. Okay, so if I am giving a signal will be here, I will get an amplified signal. Output is amplified. See this much. Here you are given this much, now you got this much. Now suppose transistor is in a saturation region. You have taken 2 points and you are giving input signal similar to this one and you got the output like this. So what happened will be here, size reduces or more or less same size. So okay, it depends upon my drawing. Okay, but one thing is sure, definitely in the active region it is get amplified. So transistor will working as an amplifier in which region? Active region. Transistor will work as a switch in which region? Cutoff region. So transistor can make use of in the 3 behavior also. 3 behavior adindada importance undu. Off state and on state transistor can use it as a switch. Transistor where behavior on active region, that region I can use it as an amplifier. So transistor will work as an amplifier in active region. Okay. So the next heading, transistor as an amplifier. Draw this diagram, only this diagram. This already we have drawn the circuit. Correct? So draw this diagram, input versus output. Transistor as an amplifier. Circuit diagram, but graph mattu. There is no difference in the graph, but still that extra AC signal adding to the existing DC signal. This is what is happening. Okay, already DC signal is there. So DC signal graph is there. So we are adding AC into this one. So this is what is happening. Okay, I hope you have drawn right. Regions cut off state, saturations, on state, active region. So actually this and on into the DC line we are giving extra what? AC. So AC is added with the DC. AC plus DC will give rise to an amplified signal. The transistor will have a three behavior: off state behavior, cut off behavior, active behavior, saturation behavior. In moon behavior transistor is having three behavior. In three different behavior I am giving input signal, same input signal into three type of character transistor. One type of character, cut off state I am giving input, then transistor is saying I am not amplifying. Then I am giving not amplifying. Then when I am giving to active region, DC given to DC line when transistor active region, during that time transistor is amplifying. So these two traits, transistor is an angry mode. This is in happy mode. So it can amplify it, it can boost the signal. Okay, so below we will write transistor act as an amplifier. Transistor act as an amplifier. Transistor act as an amplifier in active region. Transistor act as an amplifier in active region. Below right, in saturation and cutoff region. In saturation and cutoff region, transistor is not amplifying this signal. Transistor is not amplifying this signal. In cutoff region and in saturation region. Cutoff region and in saturation region. Okay. Then the next one, next up. So amplifier and switch same on transistor three type of behavior: cutoff and saturation. Transistor will work as a switch. In active region, transistor will work as an amplifier. Next one, transistor as an oscillator. Transistor as an oscillator. Oscillator means what? What is the meaning of oscillator? Oscillator means it's simply a device. Oscilloscope and oscillator, function generator. It's a device which is used to produce sine signals. What is the input of an oscillator? AC, DC. Transistor the input we are giving. If you are not giving AC, it will not amplify. Already DC voltage we are giving, and additionally we are giving AC voltage, so transistor will amplify it. Same way, what is the input of an oscillator? AC, DC. Transistor oscillator has no input. Okay, no AC, no DC. Oscillator has no input. The simple oscillating circuit is the tank circuit. Okay, so below write simple oscillator. Simple oscillator circuit. Tank circuit. Tank circuit means what? LC. L and C. Okay, LC. Now we'll see how the oscillation is produced in an LC circuit. Okay, so this is a capacitor with an inductor. Simple oscillator, example tank circuit. Now listen to the board. So now here capacitor LC. Okay, initially we are assuming capacitor is fully charged. So this plate is positive, this plate is negative. So here store charge. So what type of energy will you can have? For example, what type of energy? Electrical energy. Correct. Here. Now what happened to the capacitor? Here inductor is an empty box. Inductor doesn't contain any energy. So capacitor charged. So what capacitor will do? Capacitor will have a tendency to share the charges. So charges to whom? To the current is increasing. Now I am plotting a graph with the current versus time. I am writing as I of t means function of time, which means current is changing with respect to time. Other meaning I of. So when time is increasing now, current through the coil with respect to time. Other time which current what will happen? Current increases. So current increases. So current is keep on increases. Now capacitor is fully given its full charge. So this box is empty now. Nothing is there in the box. But who got all this energy by the capacitor? Inductor will got. So inductor stomach is now full. So inductor will have a charge. Okay. So inductor no property. Once inductor is charged, inductor will produce back EMF. With opposite EMF. And back is normal EMF in opposite. Back EMF. A back EMF will produce. Now capacitor is empty, inductor is full. What inductor will do? Inductor will start to deliver charges to the capacitor. So what capacitor will do? Capacitor is now started to store the charges, not delivering charges. So when it keeps all the charges, it is not giving to outside. So what happened to the current? Current decreases. Capacitor is now taking all the charges and storing there. When capacitor is giving the charge, it will increases. Capacitor is not giving charges. Inductor. So charge is taking by the capacitor. Charge is flow here. So capacitor is eating the charges. So what will happen? Current will be reduces like this. Increases. When current reduces to the minimum value means current reaches the maximum, which means is full of energy. What happens will be here? Empty. Nothing will be there. Completely taken. Again what will happen? Capacitor is full. Capacitor will again starts to deliver the charges. Charges keep on going. So again increases. Current again increases. Okay, this is called oscillation. Sine wave, right? Oscillator. But what is the speciality of this one means over the time. When time is going, after some time, what will happen means this pulse is something like this one, like this. Damped oscillation. Okay, damped means the amplitude short eye. Die out. That's a damped oscillation. ഒരു ഓസിലേഷനിലെ ഈ ഡാമ്പിംഗ് சொல்ற மாதிரி தான் ഫ്ലക്ച്വേഷൻ ആണ്. കറക്റ്റ് അല്ലേ? this much amplitude, this much amplitude, this much amplitude, this. So it's a fluctuation. Fluctuation is not allowed. Oscillator should always produces a consistent signal, something like this. Consistent signal. This is called undamped oscillation. Okay, I need to get a perfect sine wave. If this kind of sine wave, if I am giving to my fan will first run speed, then speed will be slow, and it will stop. That is not allowed, right? Fan always has to run with a constant speed. So which means I need an undamped signal, not a damped signal. So how I can generate? So I know an LC circuit can produce damped signal. How should I get an undamped signal? From here, what can I do to get this one? Amplifier. So an LC oscillator should be connected with an amplifier. So an LC oscillator tank circuit connected with an amplifier, together I will get what? An undamped oscillator signal. So this is an oscillator, simply it's an oscillator, LC oscillator, and this LC oscillator has no input signal. Initially a full charge capacitor will place it here. That is over. Now if you take output will be here between these two points, you signal like this. Understood? So oscillator has no input. So if oscillator has no input, how? Okay, initially I have given some charges. So how this is actually happening, how the trigger point it is given? Because capacitor want to know, I have to deliver the charges. So once the capacitor is fully charged, capacitor next duty charges. Once capacitor is started to charge, inductor will get. Then inductor will deliver to capacitor will give to inductor will give it to capacitor, and vice versa. These operations will go back and forth. Okay, that's what the signals are coming like this. So we'll write below. Initially the capacitor is fully charged. Initially the capacitor, right, by point. Initially the capacitor is fully charged. It is delivering the charges to the inductor. It is delivering the charges to the inductor over the circuit. It is delivering the charges to the inductor over the circuit. So what will happen whenever it is delivering the charges over the circuit? What will happen? Current I of t started to increase. Current with respect to time. When time increases, current also increases. I of t started to increase. Next point. After some time. Next point. After some time. Next point, after some time, capacitor is fully discharged. Capacitor is fully discharged and inductor is fully charged. And inductor is fully charged. Capacitor is storing what type of energy? Electrical energy. Coil is storing what type of energy? Magnetic energy. Yes. So electrical energy is converted into magnetic. So the inductor is fully charged in bracket, right? It is stored in the form of a magnetic energy. It is stored in the form of a magnetic energy. So electrical energy is converted into magnetic energy. Conservation of energy. Before an incident and after an incident, energies are same. Okay, then write the next point. In the next cycle, inductor starts to release. In the next cycle means next moment, inductor starts to release the charge to the capacitor. Inductor starts to release the charge to the capacitor. Capacitor in charging phase. Charging phase means what? It is storing the charges, right? So it's storing the charges. So there is no charges is not allowed to rotate in a circuit. It is just eating the charges. So what will happen? The current I of t decreases. Current I of t decreases. So this process will continue. This process will continue. Charging, discharging. This process will continue, and it produces and it produces damped oscillating signal. Damped oscillating signal. Then draw this diagram. This one. Then produces the damped oscillating signal. Then produces damped oscillating signal. Draw this diagram. This one. I of t. I of t with respect to time. I of t with respect to, and it produces the damped oscillating signal I of t. I of t, damped oscillating signal. Okay, now we'll see what transistor can do. Transistor, if transistor is an active region, it can able to amplify the coming to the transistor. So we'll draw. Now we know what is an LC circuit is doing. Now we'll connect with that. of the diagram that I explained to you. Amplifier positive feedback, beta in the bracket A equal to AV divided by 1 plus AV beta. 1 plus AV beta. F equal to 1 by 2 pi root LC. Okay, so we'll start. Okay, this is an LC oscillator. Okay, you don't want to much bother about the diagrams. Concept is important. They will not ask you to draw the diagram at all. Okay. So this is an LC oscillator. This will produce us what type of signal? Damped signals. Okay, damped signal. In short, it's quite simple. Here you will get a signal. This will produce us a damped signal like this. Okay, next what happen means this is connected with, it's the same core, which means within the same transformer one is taking as a output. Okay, transformer and output, and this is coupled with this coil. Coupled with means what changes is happening here, that will be transferred to this core also. Okay, this coil will have some changes, that changes is transferred to this core, that is called mutual inductance. Okay, between the same core and between the opposite core. So the changes what is happening will be here coupled to the base connected with the L1 dash coil. So these are coupled, means transferring to the input of the transistor. You are getting this undamped or the damped signal. You will get this damped signal which is coming to a base of the transistor. This is what type of configuration? Common emitter configuration. Grounded. In a common emitter configuration, the transistor the VBB and will adjust VCC to which region? Active region. If it is one active and you are giving a damped signal, this amplifier will do. This will amplify the signal. What it is? This will be give rise to an undamped signal. That is actually happening. So this LC oscillator will produce a damped signal. This damped signal is passed to this coil. This coil is feeding to the input of the transistor VBB VCC already adjusted, working active region. Now already the DC graph will be there. On top of the DC graph I am giving this input signal. So this input signal will be amplified by transistor and will get an output as an undamped signal. Understand? Just to be here, this pulsar. Then we write some sentence. Just to write it here. Okay, this is an undamped or damped signal. Damped means shut down. Okay, it is going to shut down. Undamped. This is undamped. This is damped signal. We can write this, but this is called damped signal. Damped signal is produced by what? LC circuit, which is coupled to where? Transistor amplifier. Then out of the transistor is what? Undamped signal. Okay. Undamped signal. We will write before that. Look in here. How many major components in the devices? One is amplifier. Another one is LC circuit. Okay. This LC circuit. What is the role of this LC circuit? LC circuit is producing this signal, and this signal is given to the L1 dash coil, and it is feedback. So I can say the AC circuit with this inductor is called a feedback network. Positive, why positive, that I will tell you later. Okay, it is called a feedback network. I will tell you why it is called positive. Simply it is called, these setup together it is called feedback network. And extra, what is this one? So you can see an amplifier, you are giving input, and output of the amplifier is is output. So output is taking into feedback network. So the input of the feedback network is what? Amplifier output. So this is into where? Input of the amplifier. This is the block diagram representation. Then one more point. There is something called a feedback factor. Okay, you don't want to learn very deep about it. It's not there in the syllabus to learn much deep. Okay, feedback factor. Feedback factor is called the beta. Gain of the transistor, whether it's a current gain, whether it's a voltage gain, whether it's a power gain, that we have to see later. So current gain, for example, current gain of the transistor, there should have some value. For example, the gain, A means gain, A called capital A is called gain, A sub B is called voltage gain. What is voltage gain? Output voltage by input voltage, that is called gain. Okay, so AV means the voltage gain divided by 1 plus AV beta. Okay, AV beta, beta feedback factor. Feedback factor means gain of the feedback amplifier. Okay, so if you do these equations, you will get A. A is the gain of this signal. Signal means output by input. Now you are giving this is the input and you are getting the final output, this one. So this is the amplified signal in the equation. Or this is an equation of an oscillator. The gain of the oscillator A is equal to AV by AV is the gain of what? Amplifier. Voltage gain of amplifier. Beta is the gain of feedback network. Okay. Next thing, it's called positive feedback. Why it is called positive? Because there is a property of amplifier. What this amplifier will do means, in a simple way, if you are giving a signal like this to amplifier, positive, negative, positive, what will get out of the amplifier? You will get phase shift will just a volt ago. Just a phase shift. The phase shift will be here 180 degree. Okay, so if who will it is producing an oscillating signal, and the oscillator, what we need actually, we need, this is the input to the, this is the input of the amplifier, this is the output of the amplifier. So this output of the back, again feedback means again feedbacking to the basic varenda signal eda, this one. So from this one, how should I get this one? I have to invert one more time. So I will given one more inversion of 180 degree so that I will get this signal. Who is rotating this two times? First time 180 degree rotated by the transistor. Second rotated by the feedback network or LC circuit. Okay. So an oscillator to be work, the phase shift between, this is the input signal, this is the final output signal, the input signal and output signal be what? 360 degree or 0 degree. Okay, this is 360 and I can call as, that is called Barkhausen's criteria. Okay, that is a scientist who proposed it, and it is called Barkhausen's criteria. Okay, Barkhausen's criteria. What is Barkhausen's criteria? The input of the signal and the output of the signal should have a phase difference of 0 degree or 360 degree. Then that criteria is called Barkhausen's criteria. Understood? That much depth is not required, but yeah, minimum stuff is required. Now we will write the things we have learned so far. Hope you have written this one. And there is one more equation. F is equal to 2 pi root LC. You know what is F? Resonant frequency or frequency. L is the inductor value. C is the capacitor value. This might be new to you, but this is already not known to you, I guess. Okay. So we will write, below we will write, LC oscillator produces damped signal. LC oscillator produces damped signal. LC oscillator produces damped signal. Damped signal, which is fed back to, which is fed back to, which is fed back to the base of the transistor, which is fed back to the base of the transistor through the coil L1 dash from L1, through the coil L1 dash from the coil L1. L1 is coupled with the coil, means mutual inductance, transferring, right? One coil changes will affect on other coil EMI. Okay, is transferring to the base of the transistor. Now we'll continue. Now the transistor amplifies the damped signal. Now the transistor amplifies the damped signal and produces what it will produces, and it produces what is the signal? Undamped signal, and it produces undamped signal. Okay, next point. The phase difference between output signal and input signal of the transistor. The phase difference between output signal and input signal of the transistor is, how much is the phase difference? 180 degree. Very, very important. Okay, of the transistor is 180 degree. The feedback network, positive feedback, the positive feedback only can produce oscillation. Okay, negative feedback circuit will be there, but it's not needed for you. So the feedback network also produces 180 degree phase shift. 180 degree phase shift. Okay, so total phase shift in the circuit, is equal to, total phase shift in the circuit is equal to 180 plus 180, which is equal to 360 degree. 180 plus 180, which is equal to 360 degree. So below, right? So to have a undamped oscillating signal, the phase shift over the circuit, is equal to 0 degree or 360 degree, is equal to 0 degree or 360 degree. This condition is called Barkhausen's criteria. This condition is called Barkhausen's criteria. This condition is called Barkhausen's criteria. Okay, hope you have drawn this diagram also. Okay, so you know what is now feedback network. So you have written this equation, A is equal to AV. So below, right, AV is the voltage gain. AV is the voltage gain of the transistor. AV is the voltage gain of the transistor. We are going to see in the next topic. Okay, so these two equations you have to remember, and based upon that we'll see. Okay, understood? Fundamental. Very simple questions will ask mostly based on either these two equations. There are no much complexity. As well as remember, this is a positive feedback, not negative feedback. Okay,